Let f be a continuous function that maps from x to y. Prove that if s is in y, so here's y here, and s is in y, and s is a closed set in y, so here's s, then prove that the inverse image of s under f, so here's our domain x, prove that this inverse image of this set, which is somewhere in here, inverse image of s, is also closed. So we want to prove that the inverse image of s is closed, given that it's the inverse image of a set under a continuous function. And remember, this corresponds really nicely to another thing that we've proved in a previous video. And that thing that we proved was prove that if s is an open set in y, then the inverse image of s is open. Now, we can leverage the fact that our rephrasing of the epsilon delta definition of continuity, we can leverage that rephrasing, since that rephrasing is rephrased in such a way that we're talking about open balls in the codomain of radius epsilon and their relationship with open balls in the domain of f with radius delta. So let me show you what I mean by that. Remember, the epsilon delta definition states the following. For any, if f is continuous everywhere, so if f is continuous at all points p naught, then that means that for any p naught in the domain of f, so for any p naught in x, and for any epsilon strictly greater than 0, there exists a delta such that if p lies in the domain of x, of the domain of f, and p is a distance away from p naught, strictly less than delta, so the distance from p and p naught is strictly less than delta, then this implies that the distance from f of p naught to f of p is strictly less than epsilon. But remember how we rephrase this. We can rephrase this in a really useful way for the purposes of this problem. So we can rephrase it in the following way. And we talked about this in a separate video, but just to review and to practice going from this definition to a newly rephrased, probably more useful version of this definition of continuity that's especially useful for this particular problem. That we can rephrase it in the following way. For any p naught in the domain of f, and for all epsilon strictly greater than 0, there exists a delta such that, and it's the same so far, but look at this, such that if p is in the open ball centered at p naught and radius delta, then this implies that f of p is in the open ball centered at f of p naught and radius epsilon. And I look at this note, I just want to remind you of this notation that I use for open balls. I use the subscript of b as the center of the open ball, and the superscript is the radius of the open ball. So check this out. If we want to show, remember our goal, we're going to take s. Our goal is to take, so first of all, we're going to take s to be any closed set in y. So take s to be any closed set in y. So just an arbitrary closed set in y, any closed set. We're not giving it any specific properties other than the fact that it is a closed set in the codomain of f. So our goal is to show that the inverse image under f of s, f inverse of s, that this set is also closed. So let me say goal here, show that the inverse image of s under f is in fact closed. Now, since our rephrasing that I'll box in orange here, our rephrasing of our definition of continuity is stated in terms of open balls, and we know something very nice that open balls are used for. We know that in an open set, any point in an open set, so let's say I have an open set U, then for any x in the open set U where U is open, for any x in this open set U where U is open, there exists an open ball centered at x in some radius r. We don't know what that radius is, but we know that it must exist such that this open ball is entirely contained in U. Every point in this open ball is also in U. And there are no points in this open ball such that there are no points in this open ball that are not in U. Okay. Okay, so now, given that fact, and given another fact that the converse of a closed set is open, check this out. If I have a closed set, I'll say S. Whoa, let me not name it an S. Let me name it, if I have a closed set A, if A is closed, then that means that the converse of A is open. The converse of A is open. So check this out. Given these two facts about open and closed sets and open balls, we can say the following. We can be motivated by these two facts to consider the converse of the inverse image of S. So, if we can show that the converse of the inverse image of S is open, then that implies that it's closed. Let me say that again. If we can show that the converse of the inverse image of the inverse image of S is open, then we've shown that the inverse image of S is closed, because a closed set must have if a closed set has a converse that's open, then that means that set, let me say this in a different way. If a set has a converse that's open, then that means that set is closed. So, this becomes our new goal, which is nice because it yields, our open ball definition of continuity applies really nicely to open sets, given the definition of an open set. So, our new goal, show that this guy's open. So if we want to show that this guy's open, we just take any point in that guy, this converse of the inverse image of S, and if we can show that there exists an open ball centered at that point, entirely contained in this set, then we're done. We've shown that this is open, therefore this is closed, and therefore closed sets in the codomain have an inverse image under a continuous function that's also closed. Okay, so let P naught be in the inverse image of S under F. The converse of that set. So we're letting P naught be somewhere over here, somewhere not in the inverse image of S. So let's map P naught over to Y, because we want to use this definition of continuity, and I have a feeling that the image of P naught under F is not going to be in S, and that's going to be useful for us, and you'll see why in a second. So the reason I have that feeling that the image of F of P naught, the image of P naught is not going to be in S is for the following reason. Remember, the definition of the inverse image of some set, I'll call it A, is equal to all points X such that F of X is in A. So check this out. If P naught is not in the inverse image of this set, then that means that F of P naught can't possibly be in S. Because if F of P naught were in S, if F of P naught was in S, then by definition of the inverse image of a set, that would imply that P naught is in fact a point whose image under F is in S. So therefore it would be in the inverse image of S under F, and it would contradict our statement that we're letting P naught not be in this set. Because remember, if P naught is in the complement, or if we have a point that's in a complement of a set, I'll just say if A is in the complement, or if X is in the complement of A, then this implies by definition of a complement of a set, X is not in A. Okay, so that's really nice for us. Because F of P naught is not an S. This implies by definition of a complement, this implication actually goes both ways. X is in the complement of A, of a set A, if and only if X is not in A. So if X is not in A, then that implies also that X is in the complement of A. So we can say the following. F of P naught is not an S, so therefore F of P naught is in the complement of S. So So that's really nice for us. So we can write f of p naught over here. F of p naught is somewhere over here. But look at this. S is closed, so therefore its complement is open. Let me say that again. S is closed, therefore its complement is open. So what do we know about open sets? Well, we know that any point in an open set, that for any point in an open set, there exists an open ball centered at that point, entirely contained in that set that we are claiming to be open. So we know that S is closed, therefore the complement of S is open. So f of p naught is just a point in the complement of S. So therefore, by definition of an open set, it must be the center of some open ball entirely contained in the complement of S. And I'm going to deliberately name the radius of this open ball a specific name. And you'll see why I do this, because it corresponds exactly with our definition of continuity. I'm going to name this radius of this open ball epsilon. So check this out. Check this out. We know now that this open ball, f centered at f of p naught and radius epsilon, is entirely contained in the complement of S by definition of an open set. So, check this out. Epsilon is a number strictly greater than 0. And let's go back to our definition. For any number, epsilon strictly greater than 0, there exists a delta. There exists a delta such that if p is in the open ball centered at p naught and radius delta, then f of p is in the open ball centered at f of p naught and radius epsilon. So check out what I can say. I can say the following. There exists some radius delta such that if, this is directly by the definition of continuity, if p is in the open ball centered at p naught and radius delta, then this implies that f of p is in the open ball centered at f of p naught and radius epsilon. So let me make a claim here. Well, you might be asking, well, what does this do? Well, check this out. If f of p, check this out, p was any point in this open ball centered at p naught. Let me just write this open ball here. Let me just write this open ball. Let's write it a little bit better than that. Let's draw it here. Here's our open ball centered at p naught. And we're saying that any point in this open ball, so p is just any point, has an image under f that's in the open ball centered at f of p naught and radius epsilon. So, I'm going to make a claim here. Claim that if f of p, or excuse me, if p is in the open ball centered at p naught and radius delta, then that implies that p is not in the inverse image of S under F. That is to say, that's the same thing as saying that p is in the complement of this set. And look at what this does. If we were to prove that this claim is true, then that means that any point in this open ball centered at p naught must be in the complement of S under F, thus implying that the open ball centered at p naught and radius delta is entirely contained in the inverse image, the complement of the inverse image of S under F. So that's our goal, to prove this claim, because if we can prove this claim is true, then we get that we found an open ball centered at p naught, which is any point in X, and we found an open ball centered at p naught that is entirely contained in the inverse image, or the complement of the inverse image of S under F, therefore showing that this set is open, and therefore the inverse image of S under F is closed, which is our goal. So, why can I make this claim? Well, check this out. We know that the open ball centered at f of p naught and radius epsilon, that every point in this open ball, because we define this open ball to be the open ball that must exist, that's entirely contained in the complement of S. So therefore, every point in this open ball is not in S. So f of p f of p must be in the complement of S, because the open ball centered at f of p naught and radius epsilon is not in S. It's entirely contained in the complement of S. So f of p is somewhere over here. F of p is somewhere over there, right? Maybe right here. So, check this out. If f of p is in the complement of S, then this implies that f of p is not in S. And check this out. If p were to be in the inverse image of S, then that means that this implies that f of p must be in S by definition of the inverse image of a set. If p were in the inverse image of S under F, then that means by definition all points x such that the image of x under F is in that set A, or in this case S, then that means the image of P under F is in S. But we just showed that every point in this open ball, and f of p is a point in this open ball centered to f of p naught and radius epsilon, every point in this open ball is not in S. So this is a contradiction. So p can't possibly be in the inverse image of S under F. Therefore, p is not in the inverse image of S under F. Because remember, if I this is true because there's two possibilities for a point P in a set X. P is either, and let's say P is an X and U is a subset of X. This is just a fact that's used very commonly in proving things like this. So if P is either in U or not in U. So if I have a set here and I have some set U, then P can either be in here or in here, and not neither. It can't be over here, because if P is in X, P is in this overarching set X. So P can either be in the inverse image of S or not in the inverse image of S. So since I just showed that the P being in the inverse image of S arrives at a contradiction, then P must not be in the inverse image of S. So therefore, P is in the complement of this set, and therefore since P is any point in this open ball centered at P naught and radius delta, then that means that this open ball centered at P naught and radius delta is entirely contained in the complement of the inverse image of S under F. So look at this. P naught was any point, and we just found an open ball centered at that point, which is any point in the complement of the inverse image of S under F. We showed that any point in this open ball must be in the complement of the set. So therefore, this open ball is entirely contained in the complement of the set. And therefore, we've just shown that the complement of the set is open, which thus implies that this set, the complement of S under F, is closed.